In this video, we're going to be continuing with the applications of integration to geometry, and we're going to be talking about solids of revolution. So let's say you have a function f of x, and you want to find a solid of revolution that is going to result by rotating this particular piece of the function between the endpoints a and b about the y-axis. So if you consider this as a piece of string, and then you just rotate it like this, you're going to end up with a shape like this, and we are going to basically make a solid out of it. So basically we're going to have this flat part, this flat edge on the bottom here, and then we're going to have this sort of curved surface on it that is going to be rotated as well. So you can consider this could be something like a machine part that you create on a lathe by doing some machining to it, or it could be something else that you use. But essentially any solid that has circular symmetry like this is a solid of revolution. And the really interesting thing about it is that we can actually find the volume of this by performing integration between a and b. So you know that if we integrate the function f of x between the interval a and b, we're going to find the area underneath that curve for the interval a and b, interval ab. So how would we form a solid of revolution? How would we calculate the volume using integration? Well, what we need to do is we need to take a little piece. So we're going to do what we always do. We're going to draw a little rectangle of area, and we're going to say that that little rectangle is going to have some very small width delta x, and the height of the rectangle is going to be the value f of x at some point of x, so we call that x subscript j. That's going to be the value of the function at that point. That's going to be the height of the rectangle. And now, in order to form this solid, we're going to have to rotate this about the y-axis. So there's going to be a perpendicular distance between the y-axis and this rectangle, and that perpendicular distance is going to be given by the point xj, because we're evaluating the function at that point. So if we grab this and you consider that we're rotating this as if it were some kind of lever, then what we're going to end up with is we're going to trace a path that is going to create a ring around the y-axis like this. So this is going to come around like this, and then this is going to come around like this, and then because it has a finite width, we also need to take into consideration the width of that particular strip. So we're going to end up with a solid that is traced by that area, this kind of solid, and hopefully that is a little bit clearer from the diagram. Now imagine that we do the same for every other rectangle that covers that area between a and b, and then what we're going to do is we're going to add those shells together. So each consecutive shell is going to cover the previous shell, and so on. So we're going to end up with a sum of shells. So each shell is going to have the following volume. We know that the area of this is going to be f of x j. So I'm just going to call this area j times delta x, and let's assume that we're going to use the same kind of width for all of them, and then we're going to rotate it. So what happens if we multiply this area by the circumference of that rotated shape, because we're just forming a circle around it. So if we multiply this area by the circumference, then that should give us the volume of that little shell. So we're going to do that. So what's the circumference of a circle? That's 2 pi r. In this case, our r is going to be given by xj. So that's going to be a radius for each point, x. So in the end, the volume is going to be given by the sum of 2 pi xj f of xj times delta x from j equals to 1 to n. So we have n number of strips that we are using, and we are going to end up with this. So this is going to give us the volume of the solids of revolution. Now we want this to be an exact value. So how do we do that? Well, we're gonna have to transform this into an integral because we want to take infinitesimals instead of just finite units of width here. So what we're going to do is we're going to let n approach infinity, and we know by definition that delta x for equally spaced points is just going to be b minus a over n. So as n approaches infinity, this is going to approach an infinitesimal quantity dx. So that means that our volume is actually going to be represented by the integral 2 pi, because 2 pi is just a constant, so I can just write it outside, from a to b of x times f of x times the infinitesimal quantity dx. So this is going to be the formula for a solid of revolution with respect to the y-axis. Now we could make the same argument about a solid of revolution that is formed about the x-axis. So let's have a shape that is like this. So let's draw our xy plane, and let's have a similar function f of x. Now we're going to have points a, b, but we're going to rotate this about the x-axis. So that means that we're going to take this whole function, we're going to rotate it about the x-axis. So we're going to have to take into consideration different points. I'm going to call this point alpha and beta. And of course, if we want to rotate it about that, to find the area, so to find the area underneath this curve, this is going to be actually the area underneath the curve g of y. So g of y is essentially the same as f inverse of x. So this is the inverse function of x. We're just going to invert that function, and now we're going to rotate it about the x-axis. Now one thing I forgot to mention is that because we're integrating from a to b, and because according to this diagram that I drew here, a is around this point and b is here, then this shell is going to have a shallow, or not shallow, a hollow section in the middle. So obviously this is going to have a hollow section in the middle that we are going to subtract, because unless we have the function having a flat part here and we rotate that as well, it is actually going to be hollow in the middle. And if we want to find the total volume of that particular solid that is not hollow, all we need to do is add the volume of a cylinder that has width 0 to a, or just radius a, to that particular volume. So that's one thing I forgot to mention about that, because if we rotate this as it is from alpha to beta, what we're going to end up with is the following solid. So this is going to be our x-axis, and it is going to have the following shape. So this is going to be like that, and it is actually going to have a hollow cylinder in the middle. So we're going to end up with this thing. It's very hard to draw in 2 dimensions, but you get the idea. We're integrating this area, so that means that we're going to have that empty area, that empty volume in the middle once we rotate it. Alright, so this is what we're going to end up with. So can you think of how we would derive this? Well, the easiest way to do it is by drawing little rectangles. This time we're going to draw them horizontally, as we usually do, for when we're integrating with respect to the x-axis instead of the y-axis. And now the width of those is going to be dy, so I'm just going to start calling things by what they are, infinitesimal quantities, so that's going to be dy. The length here is going to be given by g of y at that point, and then we're going to rotate those about the x-axis, so that's going to be 2 pi of y is going to give us that circumference. So in the end, what we're going to end up with is the volume is going to be given by 2 pi from alpha to beta of g of y times y dy. So that's going to be the volume of a solid of revolution about the x-axis. So now that we have constructed our integrals, we can actually start to do some examples. So in the following example, I'm going to show you what to do with this. So let's have a cone. Let's have a cone by drawing the following function, x, y, and then we're going to have a straight line going from 2 to 2 here. So we're going to rotate this whole area about the y-axis, like that. So what is the function here? Y equals to 2 minus x. So that's going to be the area. Sorry, that's going to be the function here. Because if you have x equals 0, that's 2. And if you have y equals 0, then that's 2. So that's our function. And what we're going to get from rotating this about the y-axis is the following. We're going to get a cone like this. And it is going to be a solid volume. So let's apply our formula. It is 2 pi from 0 to 2 of x times the function of x, which is 2 minus x dx. So this is going to give us 2 pi times, so this is sorry, let me just expand this out before integrating. This is going to be 2x minus x squared dx. This is going to be equal to 2 pi x squared minus x cubed over 3 from 0 to 2. And once we input our values here, we're going to get the following volume. Volume is equal to 8 pi over 3. So that's the volume of this cone. Now how can we check that? Well, in this example we can simply use the formula that is given for a cone, and the volume of a cone is given by pi r squared h over 3. So r is the radius of the bottom, and then h is just the total height of the cone. So in this case our h is 2, so that's 2 there, and our r is 2 as well, so that's r. So 2 squared times 2, that's 8, and that gives us 8 pi over 3, which is the same as this. So this is just one of the examples that I can show you with solids of revolution, but you gotta know that you can use these formulas for a lot of different things, and it's quite an interesting application of integration, because it means that integration is not only limited to finding areas, but it is also useful for finding volumes, and this is quite useful for when you're dealing with shapes that you might be designing or using in practice. So in the next video we're going to be talking about more applications of integration, and we're actually going to use integration to find the arc length of a function and the surface area of a solid of revolution. So we can use the same concepts we just used here, but instead of finding the volume of the solid of revolution, we're going to find the surface area. So that's what we're going to be talking about in the next video.